Chemists use light as an important probe into the structure of atoms and molecules. And since light exhibits some of the behavior of waves, it's important that you have a grasp of some of the basic principles and terminology of wave behavior. Let's begin by introducing some different kinds of waves. There's the bye-bye wave and the stadium wave, but those aren't central to our discussion here. Let's focus instead on these two kinds of waves: transverse waves and compression waves. First, transverse. In this most common kind of wave, the material moves sideways relative to the direction of motion of the wave itself. In fancier terms, the material moves in a direction perpendicular to the direction of motion of the wave. You've seen this kind of wave in action on water, perhaps in a lake, river, or the ocean. The water moves up and down, but the wave itself moves across the surface of the water in a direction perpendicular to the motion of the water molecules. To illustrate, let's consider a wave generated by wiggling a horizontal string up and down. In this representation, the black line represents the string at rest. The red line represents what happens when I wiggle the string up and down. Note that the particles of the string simply move up and down, but the wave itself moves from the left to the right. Next, let's look at compression waves, which are sometimes given the even fancier name longitudinal waves. In this case, the direction of motion of the particles in the material is the same as the direction of motion of the wave itself. This kind of wave is a little less familiar, so let's ask our friend Mr. Slinky to show us what we mean. In this little video, you see the wave proceeds from left to right, then reflects back again, the individual loops of the Slinky moving back and forth in the same direction as the motion of the wave itself. This kind of wave is responsible for sound, as air molecules move back and forth in a relatively short distance, while the sound wave moves quickly from the source to the ear. You can see the idea of sound waves represented in this cartoon here, where the air molecules are the little dots. We use certain names to identify individual parts of a wave. Here they are. First, there's the crest of the wave. For a transverse wave, this is where the wave is at its maximum height. And for a compression wave, this is where the particles are densest. Then there's the so-called trough of the wave, where the waveform is at a minimum. And finally, there are nodes in the waveform, where we are exactly halfway between crests and troughs, and where the wave has no intensity at all. Waves have certain characteristics which have technical sounding names. Let's look at a few. First, let's talk about wavelength. This is the distance between repeated points in the wave sequence. The diagram you see here shows the wavelength of a transverse wave. And you see that once we complete one wavelength, the pattern repeats itself exactly. We could begin our measurement of the wavelength at any point on the wave. We just have to measure the distance to the next identical point in the series. If the wavelength were longer, it would look like this. And if shorter, it would look like this. For a compression wave, we apply the same principle. Here's the wavelength of a compression wave. If the wavelength were longer, it would be more stretched out. If shorter, it could be more compressed. And since we used sound as an example of a typical compression wave, it's worth knowing that a short wavelength corresponds to a high-pitched sound, while a long wavelength corresponds to a low pitch. Next, let's talk about frequency. Think of a transverse wave moving from left to right. And imagine you are standing to the side watching it go by. you would see a certain number of wavelengths pass each second. That number is called the frequency of the wave. So the frequency has the units per second, written as seconds to the -1 like this, indicating the number of wavelengths per second. This unit is also called the hertz, abbreviated Hz. Some people might say cycles per second for frequency, but that's not considered cool anymore, so we just say seconds to the -1 or hertz. As an example, let's slow the waves down a little so it will be easier to count waves as they pass, and we'll give you a chance to eyeball the frequency of this wave. Fix your eye on the spot indicated by the red arrow and count the waves which pass as the counter counts off 8 seconds. So, how many waves did you count? About 3? That's what I counted, and so the frequency of this wave would be 3 divided by 8 seconds, or in other words, about 0.4 hertz. The last wave characteristic we'll talk about is amplitude. For a transverse wave, this is simply the height of the wave. You can see that for these two waves. Even though they have the same wavelength, one has a larger amplitude than the other. For a compression wave, the amplitude is indicated by how densely the particles are compacted, as you see here. For sound, the amplitude is indicated by the volume, loud or soft. And that's really all we need to say about amplitude. There is an interesting relationship between the frequency and wavelength of a wave. Specifically, the speed of the wave is equal to the wavelength times the frequency. And if you consider the units of frequency and wavelength, you can see that this makes perfect sense. Let's look. If the wavelength is in meters and the frequency in seconds to the -1, the speed will have the unit meters per second. Now, just to fancy this principle up, let's use the Greek letter lambda to represent the wavelength, and the Greek letter nu to represent the frequency. The result is this impressive-looking equation here. Lambda times nu equals the speed of the wave. And what about light in particular? Well, it's commonly known that we can represent the speed of light in a vacuum as c, right? So we end up with this important equation here. And that's one I bet you'll want to learn by heart. Now there's a special kind of wave that plays an important role in chemistry called a standing wave. Here's how it works. As you've seen already, a transverse wave, like a water wave, typically moves like this. That's not a standing wave. But let's say the wave hits a barrier and reflects back on itself. If it does so in just the right way, reflected crests line up with the crests of the initial wave, and the two waves reinforce each other like this, generating a wave with a larger amplitude. And notice that it no longer seems to move to the left or to the right. That's why it's called a standing wave. This is the kind of wave that reinforces the notes made by musical instruments like a guitar. When we talk about light waves in particular, there is one phenomenon that is especially worth mentioning here. That is the phenomenon called diffraction. I'll use this laser pointer to illustrate. Of course, when I shine the laser against the wall, it produces one spot on the wall. Not at all unexpected. But when I shine the laser beam through a plastic sheet which contains little slits which allow the light to pass through each slit separately and then recombine, I don't just get a smeared out spot on the wall. I get a very regular pattern of spots. This phenomenon is called diffraction and can be explained only if we treat light as a wave. Here's how we describe what's happening. The red tube at the left represents our laser. The light blue line represents the wall, and the black lines represent the plastic sheet with gaps representing the slits through which the light can pass. As the light passes through each slit, it fans out to create a new wave center, and all these wave centers are lined up exactly because they pass through the slit at exactly the same time. As the individual waveforms cross one another, they interfere. In places where crest meets crest, the waves reinforce one another, making the light brighter at that point. Where crest of one wave intersects the trough of another wave, the waves cancel. So let's see this in action. When the waves reach the wall, there are places on the wall where the light is bright, and places where the light waves have canceled each other out and we see no light. This phenomenon is especially important here because we will use these arguments, and specifically diffraction, in discussing the structure of the atom later on. Well, there's a lot more we could say about waves and light, but that's all for now. So long.